Mode extraction, obtaining the modes of an electromagnetic cavity, part 8. Extracting the modes, inspecting the modes, and how one can improve precision moving forward. To get the frequencies and amplitudes of the modes more precisely, we will use the second time derivative mode extraction method. This is what required that we dump in groups of 3 as we set in basic settings. To carry out this analysis, we start by going to the Analyze tab, show all the analyzers, and open Extract Modes via operator. This computes the variables needed and sets up a GUI for inputting those variables. We make sure that our simulation name is correct. We're going to analyze the electric field. We're going to use the second derivative operator to do so. And then we have to figure out the dump range. As you may recall, we started from dump 6, so the first triplet begins at dump 7. Now we have to remember what was the last dump. For that, we go back to the run log and we see that the last dump was 72. And so we put that in there. Now we have to figure out some cell sampling. Basically, we would like lots of cells to be sampled. So what we've decided to do is to sample 3 modes in each of the X and Y directions, separated by 10 cells, and the full length in the Z direction, separated by 10 cells. This works out to 34 to 55 by 10 in the X direction, 30 to 51 by 10 in the Y direction, and 1 to 392 by 10 in the Z direction. This is going to give us about 351 points. The vector space will be a vector of length 350. We choose the max number of modes to be -1, which means compute all that you can. We are then ready to do the analysis. We overwrite existing files, and we hit Analyze. One can see at this point that the analyzer is now reading in all of those dumps. This takes a few moments. And then it very quickly calculates the frequencies. But first, let's look at the singular values. In the singular values, we see that they fall off from 1 down to about 10 to the -5, and then there is a sharp drop off after that. So that's 11 modes that look like they would be reasonable. Now, in fact, in the frequencies, we seem to have found 12, although one of the modes has a very large relative error. So what is happening now, after having found the frequencies of the modes, is that this analyzer is now computing the coefficients that one uses to combine the dump files to find the modes. This does take a little while. As you can see, at the present time, we are saving mode 4. Looking back at these frequencies, we see 1, 2, 3 that are not what we expect. Then modes 3 through 9 are in a band starting at 1.477 going up to 1.497, and those are the 7 accelerating modes that we expected to find. And then we see there are two more modes, and we don't know what those are. So we're going to have to just wait and find out what those modes look like so that we can see whether those modes make sense. At this point, it has found mode 10, and it is saving that mode. The last mode that we found was mode 11, which it is now saving. And finally, the analysis has completed. With the analysis completed, we are now ready to begin visualizing those modes. So we go to the Visualization tab, we reload the data, and now we switch to Data Overview. We look at E, and we look at E2 of the eigenmode. To see the eigenmode, we're going to want to clip the plot and look through the middle. Clip it in the Y direction. Turn it around so we can see it. But now, in order to see it accurately, we're going to fix a minimum and a maximum so that we can see what's going on. And here we see dump 0 is the 0 eigenmode. One of the non-physical modes we see is down at the end groups. Dump number 1 is another mode down in the end groups. Both of those modes would probably disappear if we had an outgoing wave boundary condition for the higher order mode couplers. The next unphysical mode is the one over on the right. That's a mode in the waveguide, and it would disappear if the waveguide had an open boundary condition, which we have not done in this simulation. We then see dump 3, which is the first of the 7 modes in the accelerating band. Dump 4 has, of course, odd parity. Dump 5 has even parity again. Dump 6 has odd parity again. Dump 7 has even parity again. Dump 8 is again odd with no accelerating voltage in the central cell. And finally, dump 9 is the pi mode that one uses to accelerate particles. What about those last 2 modes? Well, dump 10 is a mode out in the waveguide with a single node. This would go away if we had open boundary conditions. And dump 11 is a mode also out in that waveguide that has 2 nodes. And this mode would again go away. Regardless, in the end, this shows the power of mode extraction, and that it finds the expected modes with high precision, along with modes that were not expected, the non-physical modes. Now, going back and looking at those frequencies, if we compare them to the paper in which this cavity was first analyzed, we will find that our mode frequencies are about a megahertz high, higher than those published in the paper. And what one would like to do is resolve that discrepancy. And the way that's done is with some sort of convergence study. We can improve our mode by changing the tessellation. The smaller the tessellation, the longer it takes to mesh, but the more accurate of a mesh you have. The other thing we could do is go up into the constants and change the resolution and put more grid cells in the cavity. Change that number, say, from 60 to 80. Of course, the simulation rapidly becomes bigger the more cells you have. Thankfully, Vorpal is highly parallel, and so this is not a problem if you have sufficient hardware. But one can also use Richardson extrapolation to take two simulations at two different resolutions and get a very accurate result for the frequency. But that is a subject for another day.